This is Chemistry, Unit 12, Gases. Here we'll look at Dalton's law of partial pressure. So if you remember John Dalton, that's the man in the image. He was an English chemist, physicist, and meteorologist. And we studied him when we were looking at the atom, right? And we looked at his atomic theory. Well, in 1801, he began to discuss his ideas on the composition of gases. And here's what he looked at. He said if you have three containers, each containing a different gas, each gas will have its own pressure. You can see it right here. Here's container 1, 2, and 3. And if you can read these are three different pressures. Each gas has its own pressure. What he said was if the gases are combined, like in this container right here, the pressure of this mixture is equal to the sum of the individual or partial pressures. So the pressure of a mixture of gases is equal to the sum of the partial pressures. So his law looks like this. We usually say PT or P total, and it's equal to P1 plus at least P2, but it could be P3, P4. It depends how many gases you are looking at. So the 3 and the 4 is going to depend on whatever situation we're talking about, but it's at least P1 plus P2. So partial pressures combined will equal the total pressure of the mixture. So let's see what this means in terms of an experiment. So if you consider this reaction right here, which first of all is not balanced, can you see how to balance it? Hopefully you pause and try and figure it out. But your zincs are balanced, it's 1 and 1. Your H and Cl though, there's only 1 of each on the left-hand side. There's 2 of each on the right-hand side, so you need to put a 2 in front. You're welcome for that refresher. Anywho, this experiment takes zinc metal, and you can kind of see it here in this image. This really looks like the setup we use at school. So you've got zinc here in this flask. You add some hydrochloric acid and you seal it, and this will start generating hydrogen gas. You actually see it bubbling, and then you'll be left with zinc chloride. Now you can actually collect this gas by what's known as water displacement. So you pass it through water and then collect it in a separate vessel. So water displacement is the technique, but as that hydrogen passes through the water, some of the water is vaporized. So the pressure of the gas that's collected is the sum of the pressure of the hydrogen and the water. Right? So your total pressure would be the pressure of the hydrogen plus the pressure of the water. See, partial pressures equals the total. Now, if you like to actually watch this, there's a little bit simpler setup that this teacher uses in this video, but you will still see the hydrogen being generated. So it's kind of neat. If you'd like to watch it, it will be posted for you. Let's try and solve Dalton's law. So how about this example? It says a mixture of oxygen, hydrogen, and nitrogen gases exerts a total pressure of 278 kPa. Okay, so that's the total pressure, or PT. If the partial pressures of the oxygen and the hydrogen are 112 kPa and 101 kPa respectively, what would be the partial pressure exerted by the nitrogen? So you've got a total pressure, you've got your first partial pressure, this is P1, the 112 kPa is oxygen, that's 112 kPa. The 101 kPa is our hydrogen, so that's P2. We're looking for P3. So you have 3 total gases, you know 2 out of the 3 partial pressures, and you've got the total. So how do you get the third partial pressure? Well, here's Dalton's law. So I have P1 plus P2 plus P3 because I had 3 separate gases. You had oxygen, hydrogen, and nitrogen. Okay, and you also have the total. You just don't know what the nitrogen is, right? You've got oxygen, hydrogen, the total, you're missing nitrogen. So that's exactly what I plugged in. The 278 kPa is my P total, oxygen's 112 kPa, hydrogen is 101 kPa. How do you get P3? Well, the first thing you want to do is just add your two partial pressures on the right-hand side. So 112 and 101 get you 213 kPa. Now this is actually addition, right? So to get P3 by itself, you need to subtract. And your final answer is 65 kPa. Okay, now if you want to follow significant figures, 278 and 213, this is subtraction. There are no decimal places, so there should be no decimal places in your answer.